All right, y'all. It's our last lesson in applications of differentiation, and we're talking about optimization. We're going to maximize our time together by learning to maximize and minimize stuff. That's actually code for solving systems of equations. So here we go. Find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. Here's what we want to do. We want two numbers multiplied together to be a maximum. This is what we call our primary equation. This is what we're trying to solve. We're going to call x the first number and y the second number. And then there's some more information given in the problem, and that is that the sum of the first and twice the second is 64. This is a secondary equation, and we're going to use this to eliminate one of the variables. So I'm going to solve for x, and I'm going to take that x and plug it back into my primary equation. You can also solve for y, it doesn't matter. So my new primary equation is 64 minus 2y, that was what we solved for x, that used to be x, times y. We now have a function with just one variable. That's lovely. So we'll take our modified primary equation, and if ever we want to find a maximum or a minimum of something, guess what we need? The derivative. So we'll take the derivative and set it equal to 0 to solve for y. Y is 16. That's the 0 of our derivative, or our critical value. And then we can use y to figure out what x is going to be. X is 32. So there's our two numbers, y equals 16 and x equals 32. We just solved an optimization problem. And of course they get more complicated, so here's some guidelines to get you going. First, read the problem carefully and draw a picture if you can. Write a primary equation, an equation that gives a formula for the quantity to be optimized. Use a secondary equation to eliminate a variable. Determine the feasible domain of the primary equation, like determine the values for which the stated problem makes sense. I'll show you what that means. Differentiate the modified primary equation to find the critical values. Whew, that sounds complicated. And then determine the absolute extrema and, as always, justify it. A rancher plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass to feed his herd. So what dimensions would require the least amount of fencing if no fencing is needed along the river? This is why we draw a picture, because that's a lot of words. So we have a river, and we have some sort of a pasture that goes up to it. And let's put some labels on that. X, and then the two sides will be Y. Step 4 of those guidelines was about domain. And so let's just make a note here that X has to be greater than 0. So make a note of that. It might come in handy later. Now, what are we trying to maximize or minimize? We want the least amount of fencing. So that would be the perimeter, right? All right, then the perimeter is x plus 2y. That is our primary equation. Now for our secondary equation, what did they tell us in the problem that would give us a clue? We need 180,000 square meters. That's area. So 180,000 equals length times width, x times y. That is our secondary equation. So let's solve for y, and we'll plug y back into the primary equation to eliminate a variable. Clean it up, and we now have a function with just one variable. Then, of course, we take the derivative. Again, if you want to pause the video and find those derivatives yourself, that's fine. I'm just going to plug through this so you can get the general idea of what we're doing. So we'll set that derivative equal to 0 and solve for x to find our critical points. So we get x is plus or minus 600. Well, this is where that domain comes in, because x can't be negative 600. So 600, that's our critical value. And if we take 600 and plug it into here, we can find our accompanying y value is 300. Now, it wants the least amount of fencing. So do you know what I haven't done? I haven't used a picket fence to check to make sure that 600 is a minimum. So let's do that real quick. So 600, if I take like something less than 600 and plug it back into my derivative equation, say 1, plug 1 in for x, then, oh, that's definitely a negative. And then something above 600 would give us a positive. Okay, so indeed, that is a minimum. And so the dimensions of the pasture would be 600 by 300. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown. What dimensions will produce a box with a maximum volume? Well, the volume of this box is going to be x times h. That is our primary equation. Now we look back into the problem and see if we can find some constraints. So the surface area has to be 108 square inches. Well, the surface area is going to be x squared plus 4xh. So the x squared, that's the bottom of the box. And then the 4xh is each of the sides of the box. That's our secondary equation. Now we can use that secondary equation to solve for one of the variables. So I solved for h. And then plug h back up into the primary equation, clean it up, and we have a function with just one variable. I think you can guess the next step is to take the derivative, set it equal to 0, and solve for x. So we get x equals plus or minus 6. We can't have a negative side length, so we're just going to use 6 as our critical value. Now let's see what 6 is. So plugging maybe a 0 into the derivative, that's plugging a 0 here, that's a positive. And then if I plug in something big like 10, I get a negative. So the function is increasing until 6 and then decreasing. So is 6 a maximum? Yes, it is. So we can plug that back in to our h, solve for h, and we have the dimensions of our box need to be 6 by 6 by 3. What are the dimensions of an aluminum can that can hold 40 cubic inches of soda that uses the least amount of aluminum? Assume the can is cylindrical and capped at both ends. So the least amount of aluminum, that is surface area. So surface area is going to be the area of the two circles, top and bottom, and then the area of the sides of the can, which is the circumference of the circle times the height. There is our primary equation. Now we need a secondary equation. 40 inches cubed, that's going to be volume. So the volume of a cylinder is the area of the base times the height, pi r squared times the height. We have our secondary equation. Now you can solve for one of the variables. And again, you can pick which variable you solve for. Plug that back into our primary equation. Clean it up. And we now have a function with only one variable. Take the derivative, set it equal to 0 to find your critical points. Wow, that's something. Good thing this is a calculator question, because if you put that into your calculator, we can get just a decimal of about 1.853 inches. So the question is now, is that radius a maximum or a minimum? Let's check. So if we plug in 0 back into our derivative equation, that'll give us a negative and a positive for anything above 1.853. So it looks like 1.853 is indeed a minimum. We wanted the least amount of aluminum, so we can plug R back into our height equation. And there we have our dimensions. All right, the last one we're going to do here is a little bit different because there's not necessarily a constraint, but there's still something that we want to optimize. So Student Council wants to sell custom snack boxes to raise funds for teacher gifts. Yay! The council president, known for his school spirit and love of efficiency, has challenged our calculus class to design the perfect eagle's nest snack box with a maximum volume. You are given a 15 by 17 inch sheet of cardboard, and your job is to create an open top snack box by cutting squares of equal sizes from the four corners and folding up the sides. So the question is, how deep should the cuts be? Wow, well, let's get a picture of what we're working with. So these corners we're going to cut off. And then these sides will just fold up, and then there we go, we'll have a box. So we have 17 inches by 15 inches. And the question is, how deep should the cuts be? So that's going to be our variable, x, which means the actual side of the box, well, on the bottom, it'll be 17 minus 2x, right? And on the side, it'll be 15 minus 2x. So the volume of a box is length times width times height. So our box, there we have length times width times height. Well, let's go ahead and multiply that out so that we have a polynomial. And if we want to maximize, then we're going to need the derivative, right? So we'll go ahead and take the derivative of that and set it equal to 0. And then if you solve that, this is a calculator question to make it a little bit easier. You get two spots, x equals 2.65 and x equals 8.02. Well, if x equals 8.02, like that is just not going to work. So that's kind of outside of our domain. But 2.65, let's just check on that one. So would 2.65 be a maximum? If you plug in a 0 to the derivative, yeah, you get a positive, and if you plug in some big number, you get a negative. So indeed, that's our way to maximize the volume of the snack box. So we'll end there. Thanks so much for being here, and gosh, I guess I'll see you in the next chapter. We'll start a new adventure on integration.